Hi, now we discuss bias reduction logistic regression. So this is a method to solve the problem when data are linearly separable. Meta estimates of logistic regression is biased. So that is expectation of beta hat is not equal to beta. So to illustrate this situation, that we think of simple case that we only have one predictor and we have binary response. So the problem of logistic regression linearly separable case is that even though we have some true curve, true fitted probability, such as this, if we only have a few observations, then it's really a kind of strange situation. You can see that even if this is the true regression curve, if we only have few observations, maybe observations can be this. This is just a typical situation. But if we only have these 6 observations, fitted curve is totally different from this red curve. Okay, so at first, this is linearly separable case. Okay, so one dimension, but a linearly separable case. And the fitted curve will be this, even its steeper curve. Okay, so even though the originally true curve is here, true data generating process is this one, but the fitted curve is here. So fitted curve is very steep, so that means the beta hat is very large. So you can see that this estimate isn't really the unbiased because it goes to infinity. And you can see that we have very small probability that beta hat goes to negative infinity. Of course, the observations are here, here, and here, and here. It goes to negative infinity, but this does not happen often under the true curve. So the idea is that if we reduce this bias, then we can automatically solve the problem happened in the previous video. And the bias reduction MLE, it's proposed by Firth in 1993 in Biometrica. So this gives another estimate, which has a smaller bias. So basically, in statistical theory, asymptotic theory, that we can approximate this beta hat as the true beta plus some bias. So expectation of beta hat is beta plus some quantity b1 over n plus b2 over n square, and so on. So this method removes the biggest bias in beta hat. And using this, actually, we can solve the problem happened in the previous video. And the calculation is very complicated, and if you want to see the details, you can see the original paper. But actually, the other results, what they did is to give this likelihood, p to the power, the 1.5 times 1 minus p to the power 1/2 for success, and this power for this, the likelihood for failure. So that is actually the rule for bias reduction logistic regression. So originally, for usual regression, this is p to the power 1, and this is 1 minus p to the power 1. So it looks like we make some base rule to make this exponent larger. So p to the 1 and 1 to 1 minus p to the power 0, that is too strong. So just we add 1/2 each, and we have a little more moderate likelihood function we define. And bias reduction logistic regression in R can be done by library BRGLM. So if you install this package and use BRGLM function, so this package gives us a warning that the BRGLM2 is developing, and it will finally replace original BRGLM package. But okay, so for now that we use the BRGLM package and we fit the species, either setosa or versicolor on sepal width and sepal length, and the family binomial. Capital iris is the iris except for the virginica, so 100 observations. Then we get the summary. Then, okay, so we have much smaller coefficients and all are significant. So this is expected because if we solve the problem of the ununiqueness, non-uniqueness, and also the diverging problem, anyway, so model can separate the two groups perfectly. So all variables should be highly significant. And actually, we get significance for these variables. Yeah, so this is how bias reduction logistic regression work. And there are some alternative methods. So another remedy for this linearly separable problem is the changing likelihood function. So likelihood function, the L of beta, so we maximize this one to get the maximum likelihood estimator. But the penalized likelihood add some other, typically the summation of beta I absolute value square. Maybe we have some parameter lambda here. So this is called the penalized likelihood. So basically, we penalize the size of beta. So then we have the finite solution for beta. So you can see that this summation is quadratic function. So you can see that we add the parabola to the likelihood function, and the parabola always have the minimum. So finally, even we add some other function L beta, still this has the minimum. So this is called the rich penalty or L2 penalty. And another popular penalty is lambda times the sigma, summation of the absolute value of beta I. So this is lasso penalty or L1 penalty. So the idea is the same. And actually for the bias reduction logistic regression, it's also almost the same as the putting some function to likelihood function to make the beta shrinks to 0. So beta smaller than the MLE. And another method is support vector machine. The support vector machine, maximize, even if we have the two separable cases, so group 1 and group 2, if we have large margin, so this line is not unique, but we think about the distance between these points, and we maximize this margin, then the method becomes stable. Yeah, and the neural network is similar to logistic regression model. So it also has a similar problem to this logistic regression linear separable cases.